Welcome back to our video module on statics. We're going to continue our previous problem. Now, what we've looked at in our previous video was this block. It's 2 feet long, 3 feet high, 4 feet wide, depending, what your orientation is here. And we took a look at the force. And we asked, well, what if we constrain this along the DH axis? We create an axis. We create a rod. How much of that force is going to push this block up? How much of it? And we found out that 0.67 of the force is going to push it up. That's an angle of 48 degrees. We took a look at that and we found how that would work. Then we took a look at moments. This is also going to create a moment. If we took a look at a moment about A, what would that moment be? And we did R cross F and we ended up with our number. And then we started doing projections by saying we're going to constrain that moment along AC. Now, thus far, these problems, the being able to do R cross F and be able to do projections, it's helped us, but it hasn't been grossly changing the nature of the problem. However, if we say we're going to constrain the axis along AG. Now this can be done with your normal, find the perpendicular distance to the axis, but it is far more labor intensive than what we're going to do. So what we're going to look at is let's pretend that we're going to take this block and we're going to run a rod through AG. We're applying the force as we said, and we're going to see how much of that force is going to want to spin the rod. In other words, what's the torque generated? Now, what we found is first we find the moment about A. So we did that. We found out that the torque generated by F about A is this amount right here. Next, we took a projection to see, well, what would happen if we were just trying to spin this around something parallel to the x-axis that goes through A. Well, we did that. That was fairly straightforward. But now what I'd like to do, now I'd like to take a look at what happens with that moment if we spin it around AG. AG. Let's figure out what the unit vector is from AG first. Unit vector AG is simply going to be the vector GH divided by the magnitude of GH. Now, the vector GH is going to be, let's take a look at the problem. 4i, 3j, well, negative 3j, and negative 2k. So that's going to be 4i, negative 3j, minus 2k. And the magnitude of those is going to be the square root of 16 plus 9 plus 4. That equals 1 over square root of 29 times 4i minus 3j minus 2k. Our next step is let's take the dot product of the moment. So we're going to end up with a moment times a dot product, AG, and say, okay, what does that equal? Here we go. We'll try and keep this all in one line if we can. 2f over square root of 13. We're pulling from right here. And that's going to be 3i plus 4j plus 6k. Take the dot product times 1 over square root of 29. 4i minus 3j minus 2k equals 2f over the square root of 13 times 29, which is 377. No, I'm not a math whiz. I just have a calculator here. We're going to do 3i times 4i. That's going to be 12. We're going to have 4j minus 3j. It's going to be minus 12. And 6k minus 2k minus 12. And we end up with negative 12 times 2f over square root. Let's move this down. $377. If you simplify that, 24 divided by square root of 377, you're going to get a negative 1.24 f. That is the magnitude of your moment. Now I want to be careful. This is a scalar. So we don't know, it's not specifying what the direction is, but we know what the direction is. We know the direction of this moment is from A to G. So if we wanted to write this out, we take this quantity multiplied by the unit vector from A to G. And we found out what that was right here. There's the unit vector from A to G. This is the magnitude of the moment. Now the negative is going to mean that it's going to, instead of, if it were positive, it would be oriented in this direction, which means that the block would want to rotate in such a way that the torque is in this direction. In fact, the torque is going to be going in this direction. It's going to be going opposite. The block is going to rotate the opposite way. If you're looking at it, D is going to want to go up. D is going to want to go towards E. Well, that means it's going to rotate about AC with the vector pointing in this direction. So that's what that negative means. So if we wanted to say if we wanted to, really dot our I's and cross our T's, we would say that the moment of F about AG equals 1.24 F, and now it's a negative, and so we're gonna kind of, I'm not gonna say be slick here, but we're gonna just reverse our signs. Actually, let's just go ahead so we can we'll keep that negative right there. 4I minus 3j minus 2k. This is the actual moment that is being induced about AG when that force is applied. Now take a look at how amazing this problem is, what we were just able to do. We were able to apply a force, and for lack of a better word, I'm going to say this is a force in any direction. You're applying a force to a rigid body, and then you're going to constrain that body. And the reality is I chose a, did I call this C or G? AG. The reality is AG, it could have been anything. I mean, it could have gone this way, it could have gone this way. We could have constrained it along any direction, any axis. This means that as long as you have a force or a torque being applied to a rigid body, if you constrain the motion, that's no problem. No problem at all. You put it in the vector form, you do your projections, and you come up with your answer. I hope this has been really helpful for being able to use projections, seeing how they're used, seeing the way they work, and even working our way through a couple simple problems. I look forward to seeing you on our next module as we move on to the next topic. If you have trouble with this, feel free to review the video a couple of times. Thinking through this in 3D can be pretty tough, and by all means, work through the problems yourself. Thank you so much, and I look forward to seeing you on our next session.